So question 1, well, part A, of course, is really easy. Two forces, it gives you the size, and they're acting in the same direction. I'm sure you all know how to find the resultant of those. For part B, they're acting in opposite directions. 9 newtons one way, 6 newtons the other way. Again, that should be really easy to find the resultant in that case. Part C, when they're acting at 90 degrees to each other. So please don't try and do this in your head. The only way you can do it is by drawing the diagram where you draw one of the forces, you draw the other one which is at right angles to it, and you find the resultant. And it's up to you whether you want to do it by scale drawing or because it's got a right angle in it. If you want to do it by Pythagoras, you find that easier, that will be the way to do it. It's up to you. Question 2. An object in equilibrium is acted on by a 3 Newton force, a 6 Newton force and a 7 Newton force. What's the resultant force on the object if the 7 Newton force is removed? Now that seemed really complicated. I was looking at that and thinking, what on earth is going on there? And then I realised that it is actually almost a trick question. The answer is very easy. And if you look in the back of the book and find the answer, is the answer. So it's an equilibrium, you take away 7 newtons, what's the resultant? Think about it, is actually a complicated way of asking a very easy question. Right, question 3. A point object of weight 5.4 newtons in equilibrium is acted on by a horizontal force of 4.2 newtons and a second force. So draw a free body force diagram. In other words, the sort of diagrams we've been doing, we haven't really called them free body diagrams. But all that means is you draw the object as a blob, you draw the forces, so it tells you its weight, 5.4 newtons. It tells you that there's a horizontal force, so you've got to draw a horizontal force, and I'm not going to do it because the question's for you to do, so you will draw a horizontal force, and it's up to you whether you draw it to the left or to the right. The question doesn't specify, so it's up to you. And then you've got to draw the third force that acts. So let's have a think what you'll have to include. There's a force acting downwards. There's a force acting, let's say that we're going to do it to the left. Force acting downwards, a force to the left, and the third force puts it in equilibrium. So that means the third force must have part of it, or one of its components, must counteract the downward force. It's got to have an upwards component. If we drew the horizontal force to the left, the third force must also have a component that cancels out that force to the left. So the third force must have a component upwards and a component to the right. So I'll leave you to draw the diagram for that. You've got to find the magnitude of F, of this unknown force. So you could do it by components. You could find its vertical component and its horizontal component, and when you've got those, you could then combine them either by doing a vector diagram or by using Pythagoras. Alternatively, if you don't like using components, you could draw a vector triangle, and you know that whatever these forces are, the downward force and the horizontal force and finally the other force must come into equilibrium. So the downward force, the sideways force if I've drawn it to the left, and the extra force that you're going to introduce must be in equilibrium, so it must take it back to the start of your force diagram. And then the second part of question 3 is to find the angle between F and the horizontal. Right, question 4 has got a diagram with it. And you've got to find the tension in each half of the wire. So what clues can we get for this? Well, the clues we can get is that each half of the wire must be supporting half of the weight. So if we don't want to, we don't have to worry about the whole situation. We can say that the vertical component of the tension in the left-hand side is supporting half of the weight. So we can very quickly know what the vertical component of the tension is. It's half the weight. Then we have to think, how does that component depend on the tension? So if we've got the tension, there's the tension T. We know what the angle is. And even though we don't know the tension, we have already found, we know what its vertical component is. Because we know that that vertical component must be half the weight. So that's T sine 12 degrees is half the weight. There is, of course, also a horizontal component, but that doesn't seem to be involved in the question. You might be able to work out for yourself, looking at the picture, what it is that balances the horizontal component in the left-hand side of the cable. Right, question 5. A ship being towed by 2 tugboats. And it tells you the angle between the tugboats and gives the force in each cable. Right, find the resultant force on the ship due to the 2 cables. So you've got 2 vectors. To find the resultant, remember the rules. Different ways of doing it. You can either draw one vector first and then draw the second vector on the end of it to find the resultant. That's one way of doing it. That's the way I prefer. Or we can do the method that is perhaps a little bit more suited to thinking about things with ropes pulling ships and stuff. And that's when we take the 2 forces, we do draw them as if they are on 2 ropes tied together, and then we remember to complete the parallelogram and find the resultant. Obviously, whichever method you use, you should get the same answer. And it's up to you whether you want to do the drawing to scale and take measurements, or whether you want to try and use trigonometry. It's probably much easier to do it to scale, because the angle's 40 degrees. You don't have any right angles, so it makes it much more difficult to use sine and cosine. So I'd probably do that one by scale drawing. Now part B, when it says calculate the drag force on the ship, that's cheating a little bit, because that's something we haven't really done. And also, the key thing in the question, it says it's at constant speed. So although we haven't really done about Newton's laws and about acceleration, always say if it's going at constant speed, it must be that it's in equilibrium. So if you've worked out the forward force due to the 2 cables, it doesn't take much working out what the backward force must be due to drag in order for the ship not to be accelerating. Right, question 6. So this is obviously a moments question. The meter rule is pivoted at its centre of mass, in the middle there, supporting a weight of 5 newtons and an unknown weight W. So you've got to calculate the unknown weight. Well, this is a very straightforward question, but please do it the way you've been told. Please start by saying total clockwise moment equals total anti-clockwise moment. And provided you use millimetres all the way through, you don't need to change to metres. If you do want to change to metres, that's fine. But if you use millimetres throughout, it will still work. Now, because the pivot is in the middle of the ruler, so the weight of the ruler acts through the pivot, that's why we don't have to worry about the weight of the ruler affecting the moments. So we've just got one clockwise moment and one anti-clockwise moment. It's in part B, when we're calculating the support force, that's when you need to worry about the weight of the ruler affecting things.